In this video, we're going to discuss the limit comparison test and take a look at some examples of how to use it. To motivate the need and use of the limit comparison test, let's consider the series from n equal 1 to infinity of 1 over n squared minus 1 and try to determine whether it converges or diverges. It's easy to see that 1 over n squared minus 1 will always be greater than 1 over n squared for every value of n. And we also know that the series from n equal 1 to infinity of 1 over n squared converges by the p-test, since this is a p-series with a p-value of 2, which is greater than 1. Unfortunately, since our given series has terms larger than a convergent series, the comparison test does not apply. We don't have any information using the standard comparison test about our original series. However, these two series are incredibly similar. They only differ in each term by a sum or difference of 1 in each denominator. And so it's almost certain that our given series, 1 over n squared minus 1, will converge since the comparable series, 1 over n squared, also converges. However, we need to be a little bit more formal than simply saying the series are similar and so they should converge. And so one way we can show two things are similar is by comparing them using a limit instead of a direct inequality, like in the comparison test. So we want to compare the terms of our given series, 1 over n squared minus 1, and the comparing series, 1 over n squared, using limits. The way that we're going to do this is we're going to take the limit as n approaches infinity of one of our series terms divided by the other series terms. So in this case, we're going to take the limit as n goes to infinity of 1 over n squared minus 1 all over 1 over n squared. We can simplify this before computing the limit. This is going to be 1 over n squared minus 1 multiplied by n squared over 1. So we're multiplying by the reciprocal of 1 over n squared. This will give us the limit as n goes to infinity of simply n squared over n squared minus 1. And we know that in order to compute limits like this, one approach is to multiply and divide by 1 over the largest power of n in the denominator, which would be 1 over n squared here. And so we get the limit as n goes to infinity of 1 over 1 minus 1 over n squared. The 1 over n squared term goes to 0, and so we get a limiting value of 1 here. And so what we've shown is that the limit when we divide our given term of our given series by the corresponding term of the comparable series, we get a limiting value of 1. Now what this means is that for large n, for large values of n, this is the limiting part as n goes to infinity, our quotient of our given term and our comparable term is approximately equal to 1. The larger n gets, the closer to 1 this becomes. And then this means that 1 over n squared minus 1 is approximately equal to 1 over n squared. Now we already knew this, but what the limit is telling us is that as n gets larger and larger, this approximation gets better and better. And so therefore, since these terms get closer and closer together, we can use that logic along with this limit calculation to conclude that both series either converge or both diverge. And in this case, since 1 over n squared converges, we know that our given series is going to converge as well. This is the idea behind the limit comparison test, which we can now formally state. So the limit comparison test says that if we have two series, the sum from n equal 1 to infinity of a sub n, and the sum from n equal 1 to infinity of b sub n, and both of these series have positive terms, then if the limit as n approaches infinity of a sub n over b sub n is equal to some number L that is not 0, then either both of the series converge or both diverge. Now there's a couple things that we should keep in mind with the limit comparison test. First, the two series with terms a sub n and b sub n, one of these is the series that we're testing to determine whether it's convergent or divergent. The other is a series that we need to come up with in order to make a comparison. And we typically use similar strategies as we did with the regular comparison test in order to come up with that second series. Another thing to note about the limit comparison test is that we don't need to know that one of the series terms is always less than or equal to the other series terms. In this case, we actually don't care about how the specific terms a sub n and b sub n compare to each other, whether one is less than or equal to the other, or larger than or equal to the other, or if they kind of jump back and forth. It really doesn't matter for the limit comparison test, because here we're not comparing them directly using an inequality, we're comparing them using the limit calculation. And so we don't care about an inequality direction for this particular test, unlike the regular comparison test, in which case the direction of that inequality is extremely important to determine whether the comparison test applies. The last thing to note about the statement of this test is that when we use it and compute the limit as n goes to infinity of a sub n over b sub n, in order to use this test, we need to obtain a number for that limit, and that number cannot be 0. So in this case, if we would take this limit of our ratio and get an infinite value or some undefined value or 0, then this test does not apply. And in that case, we would have to find a different series to compare our given series to in order to get a number there as our limit. And so if we get anything other than a number as our limit, this test does not apply. In this example, we wanted to look at the series n equal 1 to infinity of 2n cubed plus 3n over n to the fifth minus 2 and determine whether this converges or diverges. Because we have a rational function in terms of n, this suggests that one of the comparison tests is likely going to be helpful in order to answer this question. And so we start by trying to compare 2n cubed plus 3n over n to the fifth minus 2 to some series in which we know its convergence. In this case, we can focus on the leading terms of our numerator and denominator. And so if we remove the 3n in the numerator and are left with just the 2n cubed over n to the fifth minus 2, we know that this is going to be, the given term is going to be greater than this, because 2n cubed plus 3n is greater than 2n cubed. And now focusing on the denominator, something with a denominator of n to the fifth minus 2 will be greater than something with the denominator n to the fifth, since n to the fifth minus 2 is smaller than n to the fifth. And so our given series term is greater than 2n cubed over n to the fifth, which we can write as 1 or 2 times 1 over n squared. Now, we then know that this series from n equal 1 to infinity of 2 times 1 over n squared, we know this is a convergent p series, so this will converge by the p-test. And that is because p is equal to 2 here, and 2 is greater than 1. And so we have a series that we're comparing to a convergent p-series, but the inequality here is pointing in the wrong direction. In order to use the regular comparison test, we would need our given series to be smaller than our convergent p-series. Therefore, for this particular series, we don't have any choice, but we need to use the limit comparison test in order to compare these, since the inequality is pointing in the wrong direction. And to make life a little bit simpler in terms of the limit, what we can also do is often ignore any constants that occur in our comparable series. So the series we're comparing to here has the form 2 times 1 over n squared. What we're going to do is we're going to compare using limits with just the series with 1 over n squared as a term. And this series, of course, will also converge because for the exact same reason as what happens when we multiply the terms by 2, we have a convergent p-series. And so we're going to use the limit comparison test to compare our given series with the series with term 1 over n squared. And so by dividing our terms by one another and computing the limit, assuming that we get a number that is not 0, then we can conclude that the series have the same behavior. And since our comparable series converges, so will our given one. So we need to compute the following limit. We need to take our series term, 2n cubed plus 3n over n to the fifth minus 2, and we need to compare that with divide that by the term of our comparable series, which we decided was 1 over n squared. And so this can be simplified. This is going to be 2n cubed plus 3n over n to the fifth minus 2, and we're going to end up multiplying that by n squared over 1. So we can distribute the n squared there in the numerator, and we're going to get 2n to the fifth plus 3n cubed all over n to the fifth minus 2. We're having the limit of a rational function, and we can simplify this one by multiplying and dividing by 1 over n to the fifth, because the largest power of n in the denominator is n to the fifth. And so we have the limit as n approaches infinity of 2 plus 3 over n squared all over 1 minus 2 over n to the fifth. And these two terms with an n in the denominator will have a limiting value of 0. And so we get a limit here of 2, which is a number not equal to 0. And so this is exactly what we wanted to achieve. What this means, since we have a number not equal to 0, is that our two series, the one that we were given and the one that we're comparing it to, which is the 1 over n squared, they have the exact same behavior, meaning they both converge or both diverge. And since our p-series is known to converge, we can now conclude that our given series converges by the limit comparison test by comparing it through a limit with the series 1 over n squared, which is a convergent p-series. So here our series converges by the limit comparison test. In this example, we want to determine whether the series from n equal 1 to infinity of 2n squared plus 3n over square root of n to the fifth plus 3 converges or diverges. If we tried to use the regular comparison test on this series, we would run into a different type of problem than we have in the past. We'd actually find it very difficult to find a series to compare it to, regardless of the direction of the inequality sign. So in this case, if we got rid of the 3n in the numerator, we would get 2n squared over the square root of n to the fifth plus 3, and our original term would be greater than that. But then if we remove the plus 3 from the denominator, we would see that our new term would be less than 2n squared over square root of n to the fifth, and that would give us then a series to compare it to. However, if we look at these two inequality signs, we notice that they're pointing in opposite directions, and therefore we're unable to conclude from this line of algebra whether our original term of our original series is less than or greater than the term in our new series here, the 2n squared over square root of n to the fifth. And so when we're unable to determine the direction of the inequality sign, the limit comparison test will give us a way that we'll be able to compare these without having to know that direction. And so we can just get rid of this and not worry about our inequalities. What we want to do is just find a series that is approximately equal to 2n squared plus 3n over the square root of n to the fifth plus 3. We already know what it's going to be because we found it in our first line that we crossed out, but we can always find it without thinking about inequalities. We can just focus on our leading term in each of the numerator and denominator. And so here this is going to be approximately equal to 2n squared over the square root of n to the fifth. And thinking of this for when n is large, that this approximation will be true. And 2n squared over square root of n to the fifth can be thought of as 2n squared over n to the 5/2 power. So taking the square root of n to the fifth amounts to taking n to the 5/2 power. And so this results in the constant of 2 times 1 over n to the 1/2 power, or 1 over the square root of n if you prefer that notation. And we know this series here, n equal 1 to infinity, of 2 times 1 over n to the 1/2. This is a p series with p equal to 1/2. So this will be a divergent p series. So this diverges by the p-test, since it's a constant multiple of the p series with p equal to 1/2, and p and 1/2 is less than 1. And so we know that our comparing series, the series we're going to compare to, diverges. And so what we now need to do is take the limit of our series divided by the series 1 over n to the 1/2, and as long as we end up getting a positive number, a number not equal to 0, then we will be able to conclude that our given series converges as well. So we want to compute the limit as n goes to infinity of 2n squared plus 3n over the square root of n to the 5th plus 3. And we want to divide this by the series 1 over n to the 1/2. And so I'm just going to go ahead and write that as n to the 1/2 over 1 by multiplying by the reciprocal. But notice here that what we're doing is we're comparing with the series without the constant of 2, just like we did in the previous example. We're just comparing with this series 1 over n to the 1/2. And that'll make the limit a little bit easier to compute without having as that constant floating around. And so that's what we're doing here with this limit computation. And so, of course, this is the limit as n goes to infinity. When we distribute the n to the 1/2, we're going to get 2n to the 5/2 power plus 3n to the 3/2 power. So we're adding 1/2 to each of those exponents. And then, of course, we have the square root of n to the 5th plus 3 multiplied by 1, which is just the square root again. So now if we look in the denominator, the highest power of the denominator there looks to be n to the 5th, but it is inside a square root, so it's actually n to the 5/2. And so we're going to multiply and divide our series terms by 1 over n to the 5/2. And in the denominator, I'm actually going to think of that as 1 over the square root of n to the 5th, so that when we combine the square roots together, we can put all of the expressions under a single radical. And so when we go through and compute this, we're going to end up getting the limit of 2 plus 3 over n, because we have n to the 3/2 divided by n to the 5/2, and that results in an n in the denominator. And in our denominator here, we're going to multiply these square roots together, and we're going to get 1 plus 3 over n to the 5th, and that'll all be inside that square root. Our two terms with an n in the denominator will have a limiting value of 0. And so here we have a limit of 2 over the square root of 1, which is equal to 2. And again, the important part here is that that is a number that is not equal to 0. And so since we have a limit here of a non-zero number, our two series have the same behavior. We already saw that the series 1 over n to the 1/2 is going to diverge. That is a divergent p series with p equal to 1/2. And so, using the limit comparison test, we can conclude that the series from n equal 1 to infinity of 2n squared plus 3n over the square root of n to the 5th plus 3 will also diverge. And this will diverge by the limit comparison test. In this case, we're comparing it with a divergent p-series, and the limit being a positive number tells us that they have the same behavior. So our series diverges by the limit comparison test. If you'd like to try a similar example, you can pause the video and try to determine if the following series converge or diverge using the limit comparison test. We have the series from n equal 1 to infinity of 1,000 over the square root of n plus 1, and the series from n equal 1 to infinity of n to the 4th plus 5n cubed minus 1 all over n to the 11/2 power plus 70. You can resume the video and see full solutions for each series in just a few seconds. For our first series, we note that 1,000 over the square root of n plus 1 is approximately equal to 1,000 over the square root of n when n is large, and that is 1,000 times 1 over n to the 1/2 power. This tells us that we're going to compare a given series with the series with term 1 over n to the 1/2, and we know that this series that we're comparing to will diverge by the p-test. In this case, p is equal to 1/2, and 1/2 is less than 1. It's worth noting that we're using the series 1 over n to the 1/2 as our comparison series here. You could also use 1,000 times 1 over n to the 1/2, and the calculation will be fairly similar and the conclusion will be identical. When we do our comparison here, we're going to take the limit as n goes to infinity of our given series term, 1,000 over square root of n plus 1, and we're going to divide that by 1 over n to the 1/2, which is the equivalent to multiplying by n to the 1/2 over 1. We can then factor the 1,000 outside of our limit, and remembering that the square root of n is equal to n to the 1/2, we get 1,000 times the limit as n approaches infinity of n to the 1/2 all over n to the 1/2 plus 1. We can multiply and divide the numerator by 1 over n to the 1/2, since n to the 1/2 is the largest power of n in the denominator. When we simplify all of that and compute the limit, we see that we have 1,000 times the limit as n approaches infinity of 1 over 1 plus 1 over n to the 1/2. Computing that limit, we get 1, and so our total limit here of our quotient will be 1,000, which is a non-zero number. This tells us that our two series have the same behavior, and since our p series that we're comparing to diverges, the series from n equal 1 to infinity of 1,000 over square root n plus 1 will diverge by the limit comparison test. For our second example, we find a comparable series by focusing on the leading term of both the numerator and denominator of our given series. So our term is approximately equal to n to the 4th over n to the 11/2 when n is large. And simplifying using properties of exponents, we see that this is equal to 1 over n to the 3/2 power. We're going to then compare our series with the series n equal 1 to infinity of 1 over n to the 3/2. And we know that this is a p-series which converges by the p-test, since p here is equal to 3/2 and 3/2 is greater than 1. So we take the limit as n goes to infinity of our given series term, divided by 1 over n to the 3/2, which means we can multiply by n to the 3/2 over 1. We distribute n to the 3/2 across the numerator, then multiply and divide by 1 over n to the 11/2, the largest power of n in the denominator. When we do that, we get the limit as n goes to infinity of 1 plus 5 over n minus 1 over n to the 4th, all over 1 plus 70 over n to the 11/2. The three terms with an n in the denominator go to 0 when we take our limit as n goes to infinity, and we're left with simply the number 1, which is non-zero. And since we have the limit of our terms being divided by each other equaling a number that is not 0, we know the two series have the exact same behavior. Since our comparing series is a convergent p-series, this means that the given series is also converging by the limit comparison test.